Hi everyone, I'm Haoyang Li from Beijing Institute of Technology. Today, I'm going to present our research on personality-driven virtual human behavior generation. This work was done with Wang, Liang, and Yizhuo Wang. Compelling and lifelike virtual human behavior is essential for creating immersive experience in virtual reality and augmented reality. The recent adoption of LLMs generates significant interest in character personalization, particularly in 2D sandbox environments. In these settings, static traits like background and psychological characteristics are typically conveyed through natural language and psychological indicators. While LLM-based frameworks in 2D sandboxes show promise, they are insufficient for VR/AR applications. Virtual humans' personalization typically manifests in visual appearance and character attributes. Most current research focuses on the personalization of virtual human appearance, covering various aspects such as facial features, stylization, animation, and full-body models. There are still several problems in the current technology for generating personalized behaviors of virtual humans. First, current methods for generating virtual human behaviors and actions typically rely on predefined scenarios, scripts, or rules, limiting flexibility and adaptability in diverse, dynamic environments. Second, although LLM-based 2D sandbox frameworks show promise, they are insufficient for VR/AR applications because they do not adequately address the complexity of 3D virtual environments. Third, most of the studies on personalization of virtual humans have concentrated on appearance personalization, yet there are few on personalization in behavior. Our proposed method integrates the virtual human's personality traits, attributes, and 3D scene context as input to generate a long-time activity sequence. On the right is a visual animation showcasing the resulting personalized behavior sequence. The framework of our approach is illustrated in the figure. This framework integrates user-defined personality traits, attributes, and a 3D scene as inputs in Figure A to develop a personality-driven behavior generator in Figure B, which autonomously generates daily activity sequences for virtual humans in Figure C. Next, let's see the hierarchical representation of human behavior. To simplify the generation process, we adopt a hierarchical structure to represent virtual human behavior. This approach is motivated by the complexity of human behavior, which is influenced by multiple underlying factors. By decomposing this complexity into multiple levels, the model provides a clear framework for the decision-making process. We categorize behavior into 3 hierarchical levels: needs, tasks, and activities. Then, let's move on to the personality-driven behavior generator. The behavior generator is defined by 2 key modules: World State and Behavior Planner. The World State module manages critical factors that influence the behavior of virtual agents, ensuring the exhibition of personalized preferences while maintaining spatio-temporal consistency. These factors are integrated as conditions in the conditional reasoning process of the behavior planner and further utilized for behavior sampling. This approach facilitates the generation of personality-driven, long-term dynamic behaviors for virtual agents. Factors influencing the behavior of virtual humans in the world state can be categorized into 2 types: intrinsic factors and extrinsic factors. Intrinsic factors are specified by the user and include the personality traits and attributes of the virtual human. We adopt the Big 5 personality traits to represent these characteristics. Attributes include physiological characteristics, social attributes, as well as hobbies and preferences. Extrinsic factors are influenced by individual characteristics and spatio-temporal features. We define time, completed activities, and 3D scene information as extrinsic factors. These elements enhance the temporal relevance and contextual adaptability of virtual human behavior, thereby improving the personalization and adaptability of activities across different scenarios. Regarding the 3D scene, we divide it into 3 main components: agent information, object information, and scene description. Agent information includes the current position of the virtual human and the orientation vector. Object information describes the shortest navigable path and distance between all objects and the virtual human. Scene description represents the structural information of the 3D environment where the virtual human is located. We employ a dynamic scene graph, DSG, to represent 3D scenes and pass the DSG into natural language descriptions to provide contextual information about the environment. It includes the containment relationships among rooms, places, and objects, as well as the connectivity between different places. To facilitate this process, we have developed a corresponding generation tool in Unity, which enables the creation of DSG for 3D scene and its visualization within the environment. Next, I will introduce the condition reasoning process and behavior sampling methods in the behavior planner. The figure illustrates the condition reasoning process. To infer the necessary conditions from information in the world state, the behavior planner employs a large language model for multifaceted reasoning. First, based on personality traits, the LLM queries the virtual character's personality attributes and determines these traits according to specific scores across 5 personality dimensions. Regarding attribute information, the LLM generates insights into the behavioral tendencies, daily preferences, and personal habits of individuals possessing these attributes within a family environment. Temporal information and completed activities are integrated as extended instructions. For 3D scenes, the LLM extracts scene descriptions, the virtual character's current location, information about all objects in the scene, and the shortest navigable distance between objects and the virtual character. Under detailed conditional guidance, we further request the LLM to predict selection probabilities to facilitate the selection of specific nodes at each layer. The element with the highest probability in each layer is selected. The figure illustrates the detailed prompts and conditions. The processes at each layer are as follows. For the needs layer, we adopt the first 3 levels of Maslow's hierarchy of needs, where the intensity of each need dynamically varies over time. The LLM evaluates the urgency of the 3 needs based on their current intensity and classifies them into selection probabilities. For the task layer, given a corresponding need, we use all conditions except for the 3D scene to predict the execution probability of task elements. For the activity layer, given a specific task type, we utilize all available conditions to predict the execution probability of activity elements. After selecting the most probable activity, these predictive variables are further used as combined inputs to predict the most likely objects chosen for completing the activity and to estimate the required time. To validate the effectiveness of our framework, we analyzed the behavioral sequences of virtual agents with contrasting personality traits in different scenarios and conducted experiments through user studies. In this experiment, we focused on 2 key personality traits: openness and conscientiousness. We applied this approach to 2 distinct 3D home environments and defined 2 contrasting personality types for each trait, generating 2 sets of personality combinations. Subsequently, we predicted the full-day behavioral sequences of virtual agents exhibiting these 4 personality types in both scenarios. All 4 virtual agents were assigned the same attributes: a computer science student who enjoys home workouts, music, and singing. From the overall behavioral trajectories shown in Scene 1 and Scene 2, it is evident that as scene complexity increases and the number of interactive objects grows, personality traits become more pronounced in the agent's behaviors. These results reveal significant differences in behavior selection, activity sequences, and object interactions among virtual agents with different personality traits. We conducted a user study through experiments to validate the effectiveness of our framework from the perspective of general users. We recruited 14 participants from diverse age groups, professional backgrounds, educational levels, and social experiences. To evaluate the impact of different conditions on virtual agent behavior generation, we designed an experiment consisting of 7 comparative methods. By systematically removing or retaining specific conditions, we analyzed the key role of these factors in behavior generation. For behavior sequence generation, we first collected personality and attribute data from the 14 participants with personality traits quantified using the enhanced BFI2 scale. Based on each participant's personality and attribute information, We generated 7 different behavior sequences, simulating a full day's activities, leading to a total of 98 behavior sequence outputs across 14 participants. The figure presents a visualization of one participant's behavior sequence under the 7 conditions. Each sequence represents a time period, with different colors denoting different activities. Additional behavior sequence results are provided in the supplementary materials. We examined the statistical significance of user rating analysis, and the results indicated significant differences in terms of behavioral rationality and personality alignment. Furthermore, we conducted a detailed analysis of the differences among various methods. Each participant evaluated 7 behavioral sequences based on their personality and attributes. The results were presented through video demonstrations, and participants assessed them according to 1. The rationality of the behavior, and 2. Its compatibility with their personality. We employed the Friedman test to analyze the statistical significance of user ratings, and the results indicated significant differences in terms of behavioral rationality and personality compatibility. Furthermore, a paired comparison was conducted using the Wilcoxon signed rank test to further analyze the differences among the various methods. The methods marked with the red box have a significant difference. For a more detailed analysis of the results, please refer to our paper. Subsequently, participants were asked to evaluate which object preferences under the 2 conditions aligned more closely with their own characteristics. The results showed that 11 participants considered the preferences generated by our method to be more consistent with their tendencies. This finding suggests that our approach not only captures general preference patterns, but also demonstrates personalized object selection, thereby enhancing the personalization of virtual agent behavior. To demonstrate the practical applicability and scalability of our personality-driven behavior generation framework in virtual humans, we extended its implementation to virtual reality and augmented reality environments. Furthermore, we applied it across multiple domains, including healthcare, education, and gaming. When extended to VR and AR environments, virtual humans can interact with objects in the virtual environment and directly engage with users. As shown in Figure A, the virtual human transitions from the activity of reading to chatting with the user. The user's position and the forward vector are obtained in real time via VR devices and integrated into the 3D scene as an object. Figure B illustrates the application of virtual humans in an AR environment, where real-world scenes are scanned and reconstructed into a 3D representation using the DSG dynamic scene graph structure. The example illustrates the activity sequence of a virtual human acting as a doctor in an AR ward environment while performing tasks. The doctor enjoys communicating with patients and demonstrates a high level of concern for their condition, showcasing the virtual human's ability to flexibly adapt to dynamic changes. The figure presents an example of a virtual human acting as an extroverted teacher who enjoys discussing with students. It demonstrates the ability to adjust its interaction style based on the classroom atmosphere and predefined personality traits. Our approach is also applicable in gaming for generating personality-driven behaviors for non-player characters, NPCs. The 2 images illustrate examples of virtual characters acting as NPCs, where each NPC generates behaviors consistent with its predefined personality traits. For instance, the character in the left image is defined as a silent and cautious guard, while the one in the right image is characterized as a lively and communicative mage. This implementation enhances NPCs with stronger personalization and interactivity, transforming them from simple pre-scripted roles into intelligent entities with dynamic behaviors. In summary, the main contributions of this paper are as follows. First, we introduce a novel task of generating long-term behaviors for virtual humans in 3-dimensional environments that effectively convey specific personality traits. Second, we develop a framework that can automatically generate human daily activities in an auto-regressive manner. This allows the generated behaviors to simultaneously reflect the desired personality traits and adapt to the dynamic 3D environment. Third, we conduct extensive experiments to evaluate the efficacy of the proposed framework thoroughly. Additionally, we demonstrate the versatility of our approach by applying it across various new application scenarios. Thank you so much for listening to this presentation. Feel free to reach out if you have any questions.